Hello, everyone, and welcome to this mini lecture. In our daily lives, we often use a ruler to measure the length of objects. The millimeter scale on the ruler helps us obtain precise measurements. But in industrial vision systems, how can we achieve high precision measurement? Now, let us begin the lesson and learn together. This lesson primarily covers the following topics. Through our study, it is hoped that you will achieve the following teaching objectives. Let's begin by understanding what a pixel is. In everyday life, the size of an object is measured using tools. For example, measure the length of a book with a ruler. If the smallest scale of the ruler is in millimeters, we can read it to measure the object's length with millimeter level accuracy. In vision systems, each pixel acts like a scale unit. Through XY calibration, we can determine the real-world physical size each pixel represents in the calibrated plane. Therefore, we only need to determine pixel distances using image algorithms, and through simple calculations, we can derive the real physical dimensions. In industrial vision systems, pixels are the basic units of images. Their resolution, physical size, and positional accuracy directly affect the system's capabilities in measurement, positioning, and inspection. So, what are the basic concepts of a pixel? Pixel, the smallest unit of a digital image, containing brightness, grayscale, or color information. Pixel coordinate system uses the top left corner of the image as the origin, with the horizontal axis as the U-axis, and vertical as the V-axis. Resolution, the total number of pixels in an image. Pixel size, the physical size of a pixel on the camera sensor. Now, let's learn about pixel precision. Pixel precision refers to the real-world size represented by a single pixel. It is calculated by dividing the field of view by the resolution. For example, if we use a 5-megapixel black and white camera with a resolution of 2448 by 2048 and a field of view of 100 millimeters on the long side, as shown, the real size represented by each pixel is approximately 100 millimeters divided by 2448 is equal to approximately 0.04 millimeters. That is, a pixel precision of about 0.04 millimeters. As shown in the diagram, each point in the real physical plane corresponds to a point in the camera image. The points A and B on the physical plane correspond to the points A and B in the image. If the distance between points A and B in the image is measured to be 300 pixels, then the actual physical distance between points A and B in the real world is calculated by multiplying the pixel distance by the pixel resolution. That is, 300 times 0.04 equals to 12 millimeters. Now, how do we use the circle finder tool? Let's take a closer look. In the Calibration software, the steps to use the circle finder tool are as follows. 1. Add the tool. Add the Find Circle tool to the tool group and open its parameter settings window. 2. Register image. Click Register Image and use the ROI to select the area containing the circle. For instance, when detecting the center circle of gear, select the center of a gear. 3. Set parameters. Choose a search direction, such as from outside to center. Set search polarity based on the circle's contrast. For example, if the outside of the circle is white and the inside is black, choose black to white. 4. Execute. Click the Execute button to detect the circle. The tool will output related information such as the diameter. Next, let's look at how to perform PLC homing and position setting. 1. PLC homing. Step 1. Set homing parameters. Open the Calibration PLC interface. Find the motion control or function section, and set parameters like homing speed and direction. For example, the speed could be 500 millimeters per minute, and the direction depends on the mechanical structure and motion needs. Step 2. Connect the homing sensor. Properly connect the homing sensor to the PLC input port and configure the corresponding input point in Calibration so that it receives the signal. Step 3. Execute homing. Use the homing button or send a command. Click or send in command to trigger the PLC homing action. The PLC will control the motor to move in the set direction. Once the sensor signal is detected, the PLC decelerates and stops the motor, completing the homing process. 2. Set position. Step 1. Determine target position. According to specific process requirements and production workflow, calculate or determine the target position coordinates that need to be set. These coordinates must correspond to the coordinate system of the motion axis controlled by the PLC. Step 2. Input position parameters. In the motion control settings of Calibration, input the absolute or relative position. The absolute position value can be directly input, or the relative displacement value can be set according to the current position. Step 3. Execute positioning. After setting the position parameters, select the Positioning Execution button in the software interface or send the positioning command. The PLC will control the motor to move to the specified position based on the input parameters and motion control algorithm. The specific operations of different brands and models of PLCs in the Calibration software may vary. When actually operating, it is necessary to refer to the technical manuals of the corresponding PLCs and Calibration software. Finally, let's study how to use the XY calibration tool. 1. Determine a reference point. Select a clear, easily identifiable and locatable point within the workspace as the reference point. Record its real-world XY coordinates in the physical coordinate system. 2. Align the camera. Adjust the camera or related equipment to ensure the reference point is centered in the camera's field of view. In the Calibration software, record the pixel coordinates of the reference point at this moment. 3. Set the offset. Calculate the XY directional offset based on the reference point's actual coordinates and its image, pixel, coordinates. Enter this offset into the coordinate transformation parameter settings in the software. 4. Verify and adjust. Move the camera or the object to different positions, then remeasure the coordinates of the reference point or other known points. Compare the actual values with the software calculated ones. If there are discrepancies, adjust the offset or check for errors in the operation. 5. Set the parameters. Open the auto calibration interface in the Calibration software. Set camera parameters such as exposure time and gain. Also set relevant calibration parameters, like the number of images to capture and the XY axis movement step size, according to actual conditions. 6. Automatic capture and calculation. Click the Start Calibration button. The software will control the devices to move and capture images at multiple positions according to the set parameters. It will then automatically analyze the feature points in the images and calculate the XY calibration parameters. 7. Save the results. After calibration is complete, the software will display the results. Save the calibration parameters for future use. This section mainly explains how XY calibration is implemented. The sizes of feature points in the image are obtained using the Circle Finder tool, which can detect the diameter and radius of a circle within the selected ROI. The actual sizes can be directly read from the calibration board. In the XY calibration tool, the pixel distances in the image are linked with actual distances through dimensional data, enabling the calculation of the real-world physical size represented by each pixel. The validation process involves comparing the real size of the feature points with the measured values in order to verify whether the calibration results are accurate. Everyone, While mastering these technologies, we should also recognize that industrial vision systems are of vital technical support in modern industry. They play a key role in enhancing manufacturing capabilities and realizing intelligent manufacturing. As future engineers and technical professionals, we should uphold the spirit of excellence and continuously improve our professional competence, contributing to industrial modernization and technological advancement. This lesson is now concluded. Goodbye, everyone.